Programming languages are the languages of the future. They are how we talk to machines, how we tell them what to do. Just like spoken languages, some programming languages are more popular than others. And then there's Python. Python is like the Swiss Army knife of programming languages. It's versatile, easy to learn, and incredibly powerful. From powering Google searches to helping scientists understand the universe, Python is everywhere. It's the language that's shaping our digital world. One reason is its simplicity. Python's syntax is clear and concise. It's designed to be readable even for beginners. Another reason is Python's vast ecosystem of libraries and frameworks. These provide ready-made solutions for various tasks. This saves developers time and effort. But Python's story is more than just technical details. It's a story of innovation, collaboration, and a bit of serendipity. So, buckle up as we journey through the fascinating story of Python, from its humble beginnings to its global dominance. Our story begins in the Netherlands in the late 1980s. Guido van Rossum, a programmer at the Centrum Wiskunde en Informatica, was frustrated with the limitations of existing programming languages. He wanted a language that was easier to read, write, and maintain. Van Rossum had been working on a language called ABC, which was designed to be simple and easy to learn. But ABC had its own limitations. It was not very flexible, and it lacked some features that Van Rossum felt were important. Inspired by ABC's philosophy but determined to overcome its limitations, Van Rossum set out to create a new language. He wanted a language that was both powerful and accessible, a language that could be used by both beginners and experts alike. In December 1989, during his Christmas vacation, Van Rossum began working on his new language. He named it Python, not after the snake, but after his favorite comedy group, Monty Python's Flying Circus. The name reflected his vision for the language: playful, irreverent, and capable of great things. In February 1991, Van Rossum released the first version of Python, version 0.9.0. Python was an interpreted language, ideal for rapid prototyping and experimentation. Python embraced a philosophy of code readability. It used indentation to structure code blocks. Python 1.0, released in January 1994, introduced functional programming tools. These features allowed developers to write more concise and expressive code. The release of Python 1.0 marked a significant milestone. As Python gained popularity, its community grew, and so did the demand for new features. In response, Van Rossum and the Python development team released Python 2.0 in October 2000. Python 2.0 introduced list comprehensions, a powerful feature borrowed from the functional programming paradigm. List comprehensions provided a concise way to create and manipulate lists, further enhancing Python's expressiveness. Another significant addition in Python 2.0 was garbage collection. This feature automatically managed memory allocation, freeing up developers from having to manually allocate and deallocate memory. This made Python even easier to use, especially for large projects. Python 2.0 solidified Python's position as a leading programming language. Its clear syntax, versatile nature, and expanding community made it a favorite for a wide range of tasks. Section 5. The Great Divide, Python 3.0 and beyond. In December 2008, Python underwent a major transformation with the release of Python 3.0. This new version aimed to address some of Python's long-standing design flaws and inconsistencies. One of the most significant changes in Python 3.0 was the introduction of Unicode support for strings. Unicode is a universal character encoding standard that can represent virtually any character from any language. This made Python more suitable for internationalization and localization. However, the transition to Python 3.0 was not without its challenges. The changes introduced in Python 3.0 were not backward compatible with Python 2. This meant that code written in Python 2 would not necessarily run on Python 3 without modification. This incompatibility created a rift in the Python community. Some developers embraced Python 3, while others remained loyal to Python 2. This division would persist for many years, causing confusion and frustration for developers. Section 6. The two-headed serpent Python 2 versus Python 3. The coexistence of Python 2 and Python 3 created a dilemma for developers. Should they stick with the familiar Python 2 or migrate to the newer but potentially incompatible Python 3? Many developers chose to stay with Python 2, especially those working on large legacy codebases. Migrating to Python 3 could be a time-consuming and error-prone process, and the benefits did not always outweigh the costs. Meanwhile, new projects and libraries started adopting Python 3, taking advantage of its improved features and cleaner design. This led to a situation where both versions of Python were actively used, albeit for different purposes. The Python community recognized the need to bridge this gap. Efforts were made to improve compatibility tools and to encourage developers to migrate to Python 3. However, it would take many years for Python 3 to fully supersede Python 2. Section 7. Wrestling with the Jill Python's performance puzzle. While Python excelled in ease of use and versatility, it lagged behind other languages in terms of raw performance. One of the main culprits was the Global Interpreter Lock, or GIL. The GIL is a mechanism used in CPython, the most popular implementation of Python, to ensure thread safety. In essence, the GIL prevents multiple threads from executing Python bytecodes at the same time. This means that even on multi-core processors, Python threads often end up taking turns rather than truly running in parallel. The GIL simplified Python's internal design and made it easier to integrate with C libraries. However, it also limited Python's ability to take full advantage of modern multi-core processors, especially in CPU-bound tasks. Despite the GL's limitations, Python remained a popular choice for many applications. Its strengths in ease of development, rapid prototyping, and its vast ecosystem of libraries often outweighed its performance limitations. Section 8. Python's Playground, from Web to AI. Despite its performance quirks, Python's versatility allowed it to thrive in various domains, becoming a cornerstone of the tech industry. In web development, frameworks like Django and Flask leverage Python's simplicity and power to build robust and scalable web applications. Python's ability to handle complex data structures and interact with databases made it a natural fit for web backends. Python's accessibility and extensive libraries also made it an ideal language for scientific computing. Libraries like NumPy, SciPy, and Matplotlib provided powerful tools for numerical analysis, data visualization, and scientific simulations, empowering researchers in various fields. Python's rise to prominence coincided with the resurgence of artificial intelligence. Its clear syntax, extensive libraries, and thriving community made it the language of choice for developing and deploying machine learning models. Libraries like TensorFlow, PyTorch, and scikit-learn provided the building blocks for a new generation of AI applications. Section 9. Python in the Classroom, a tool for learning. Python's simplicity and readability made it an ideal language for beginners, leading to its widespread adoption in education. Introductory computer science courses embraced Python as their language of instruction, introducing students to the fundamentals of programming in a clear and concise manner. Python's interactive mode and immediate feedback loop made it easier for students to experiment with code and learn from their mistakes. Beyond computer science, Python found its way into classrooms across various disciplines. Scientists and engineers used Python to analyze data, visualize results, and automate tasks. Humanities scholars leveraged Python's text processing capabilities for linguistic analysis and digital humanities research. Python's accessibility and versatility democratized programming, empowering individuals from all walks of life to learn how to code and apply their skills to solve real-world problems. Section 10. Python's Critics, a language under scrutiny. Despite its widespread popularity, Python was not without its critics. Some argued that its beginner-friendly nature masked potential pitfalls for more experienced programmers. One common criticism stemmed from Python's dynamic typing system, where variable types are checked at runtime rather than at compile time. While this allowed for greater flexibility, it could also lead to unexpected errors that were harder to debug. Others pointed to Python's reliance on indentation as a potential source of confusion. While indentation improved code readability, it could also lead to subtle syntax errors, especially for programmers accustomed to languages that used braces or keywords to delimit code blocks. Despite these criticisms, Python's strengths continued to outweigh its perceived weaknesses for many developers. Its ease of use, vast ecosystem, and thriving community made it a compelling choice for a wide range of applications. Section 11. Python's future, still slithering strong. As of 2024, Python continues to evolve, driven by a vibrant community and the tech industry's demands. The rise of data science and machine learning has solidified Python's position. Python remains at the forefront of innovation. Efforts are underway to address Python's limitations. Projects like PyPy aim to improve Python's performance. Python's community plays a crucial role in its success. With a global network, Python adapts to emerging technologies. Python will continue to shape the technological landscape.